we have one of our most important tools in understanding the nuclei is the number of neutrons to proton. So it's the neutron to proton ratio. That is probably the most important thing. And it answers a very important question. It answers the question, what do the neutrons do? What is the role of the neutron? Okay, so what we're really trying to do here is that we're trying to answer two questions. So the first thing that we got to do is that we got to start talking about the neutron to proton ratio. And when you see me write it, I'll typically write it as n/p. And then sometimes when I'm not thinking, I'll write it n double dot p. So n, the ratio to p. And this is a huge, huge thing that then really tells us what is going on inside the nucleus. And man, is this stuff interesting. So what we want to do here is that we want to start by really trying to get a good handle on what is going on. And again, we need that band of stability to really tell us. So this time I'm going to make this bigger because we want to look at some of the details. Okay, so let's start looking at this. When we look at the black band of stability, we clearly see which nuclei are stable. And one of the most telltale things about stable nuclei is that there are more neutrons than protons as the nuclei get heavier. So writing this down, I'll say that when we look at stable nuclei, the band of stability clearly shows that one needs more neutrons than protons for heavier nuclei. So look at the curve. If you look at the curve, look what the curve is actually doing. So when you look at this curve, what you're seeing here is that you could see that the curve is actually bending away. You're following this curve, and you could see that it curves away from the line that says equal number of protons and neutrons. So when you look at this purple line, this is n equals to p. So this line is telling you that we need more neutrons than protons for heavy nuclei. So if that's the case, then we really got to look at this in more detail using this neutron to proton ratio to tell us what is going on. And what you're going to see here, 3 of the most important nuclei on the periodic table are these. Are 3 important nuclei. And the question that we want to answer is why? One, without any doubt, has to be lead. Lead is number 82. So why is this important? Because this is the last stable nuclei. That's why that's important. And then the next one is bismuth. So why is bismuth important? Well, that's 83. Bismuth is important because it's the first unstable nuclei. And then the next one is uranium. And uranium is 92. So why is uranium so important? It's the last naturally occurring nuclei on Earth. Okay, I should have doubled R the occurring. I'm not going to change it. So these are big ones. If, as far as nuclear physics is concerned, these are really big ones because they tell us what is going on inside the nucleus. So the first thing that we want to do here is that what we're really asking this question as we try to look at this neutron-proton ratio. This is what drives it. What configuration of protons / neutrons make nuclei stable? There has to be some combination, right? There has to be some combination. And the way we do this is that we look at the band of stability and compare the neutron to proton ratios. That's what we do. And this guy, once again, is this NP number. So when I look at this NP number, NP then means it's the number of neutrons divided by the number of protons. And when we look at these things, you'll see what they mean here. So when I look at that band, even though I've already said this, I'm going to say it again. What we see here is that when we calculate different NP ratios for different nuclei, that ratio better give us the trend of the band of stability. So what we want to do here is to get a sense of these regions here. What I'm going to do here is that I'm going to start looking at midweight, a lightweight, midweight, and heavier nuclei. So what do I mean by lightweight? Okay. So let me write this first so that I'm at least guiding you a little bit better. So let me find my mouse. So what we want to do here is that we want to calculate the NP ratio for different nuclei. And what we're going to look at is we're going to look at lightweight, midweight, and heavy nuclei, okay? And what you're going to see here is that when we calculate this thing, you're going to see that there will be a trend for nuclei on this band of stability. So just kind of look at the picture right here. If you look at the band of stability, note that there's what would I call lightweight. So let's get some lines in here. So the first thing here is that look at the weight, the ones for 20 here. So if you look at from 0 to 20, note that the line is linear here, so the number of neutrons and protons look like they're about the same. So what I would say here is that I would say that for nuclei between 1 and 20, this represents the lightweight nuclei. So this region right here is telling me that this is this lightweight here. And then what you're seeing here is then if I start to look at the midweight ones, let's say sort of like from 20 to about 50. So this range varies, okay? So note that I'm just trying to give sort of like a trend of where we're going. But I would probably, if I look at this thing here, what I'm really seeing here is that I'm seeing that maybe around like 60, 20 to 60. There's a little bit of a shift here. Now, again, this is slippery business. So I'm not trying to give you hard numbers, but I'm just saying, if you look at this region, so what we said here is that this region is the lightweight. And what I'm saying is that in this region right in here, roughly in this region, we're seeing that this is then going to be the midweight region. Now, the reason why I call that the midweight region is that because as I get above this, then you really see that the curve dramatically changes. And as the curve dramatically changes, it really starts to curve upwards. And so this region right in here, roughly, I would call this the heavyweight nuclei. So that's really what we want to understand here. So remember, these numbers are rough here. So I'd say that maybe, so for nuclei 20 to let's say about 65, I'm going to say that's about midweight. And then for nuclei 66 to about 92, I'm going to call them heavyweight. So let's go look at these guys. So what I did here is I selected objects in this region. I say objects, I really mean atoms, nuclei. So the first one that we want to look at is that we want to look at lightweight, light nuclei. Okay, light nuclei. So if I look at light nuclei, probably the first one is that I want to pick the heaviest one on our line. So if you look at this, 20 really looks like it's right at the edge, and then it starts to curve away. So let's look at 20. So if I look at 20 protons, this is calcium. So let's look at calcium, and let's calculate the neutron to proton ratio. So when I look at this, this is 40, 20 calcium. And then we could just calculate these. So this has 20 neutrons. This has 20 protons. So if I calculate that ratio, you see that the neutron to proton ratio is then going to be 20 over 20. That has 1. So what's special about 1? That means when I look at any nuclei that are light like this, their NP ratios essentially say that the number of neutrons and protons are equal. So this tells us here that what we're seeing here is that light nuclei usually have equal numbers of neutrons and protons. So let's go to the next one. So if I go to the next one, now we're going to go to midweight. So if I look at the next midweight one, let's look at silver. And I'm just randomly picking these guys up here. So if I look at silver, I'll make this a little bit bigger. Now, where does silver land? Well, if I come up here, it's 47. So you could see that 47 is right smack in the middle of this midweight region. So what does the number for silver look like? So if I look at silver, you could see that this is 108, 47. And if I calculate the number of protons and neutrons, I get 61, and then I have 47 protons. Now you're seeing a shift here. So when I look at the neutron-proton ratio, this is going to be 61 over 47, and that number is 1.3. 1.3. Now, why is that important? What that tells us here is that there are 30% more neutrons than protons. So that means in order for midweight nuclei to be more stable, you have to include roughly 30% more, right? So in other words, to be stable in this region, nuclei require about 30% more neutrons than protons. So because there's a range here, if you come back up here, because there's a range, so if this is 1-to-1, so they're exactly the same, but as you go down towards 20, then that 20% could be 10%, it could be 20%. Or if I start to come up towards the heavy end, it could be 40%. So the ratio is changing for these guys. Okay, so there's a range that what we're finding with these guys here. So let's go look at the next one here. So if I look at the next one that I have here is lead. So then I would consider lead to be a heavy nuclei. So if I put in my lead, look what I'm seeing here. You're seeing that when I calculate this ratio, it's 207, 82, and then I subtract them. So I get 125 neutrons, and then this is 82 protons. And so when I look at this ratio, you see that this thing then is 125 to 82, and this number is 1.5. Again, what does that number mean here? It means you need 50% more neutrons than protons. So that's effectively the maximum ratio of protons to neutrons that you could have. Now, I only did this to 2 sig figs, so you'll see that it's a little bit different than that. So what you're seeing here is that for heavy nuclei, one requires 50% more neutrons than protons. I don't know why I wrote that twice. I didn't really mean to do that. So it turns out that 50% is the maximum. Why? Because lead is the last naturally occurring element here. So you see that this thing then is a 125 to 82, and this number is 1.5. Again, what does that number mean here? It means you need 50% more neutrons than protons. So that's effectively the maximum ratio of protons to neutrons that you could have. Now, I only did this to 2 sig figs, so you'll see that it's a little bit different than that. So what you're seeing here is that for heavy nuclei, one requires 50% more neutrons than protons. I don't know why I wrote that twice. I didn't really mean to do that. So it turns out that 50% is the maximum. Why? Because lead is the last naturally occurring element here. So if I come into the band of stability now, okay, if I look at the band of stability, what do these numbers show here? So the band of stability, so how does this look like on the band of stability? So then when I look at this thing here, if I punch this guy in here, so I'm going to expand this a little bit, but not too much. I think I might put it over here instead. Let's go look at the numbers. There's the calcium. Let's look at calcium. So if I look at calcium, calcium is 20, right? If I look at calcium, right, maybe I should bring this guy down. So if I look at calcium, we could see that calcium is 20. So if I look at this thing, it's got to look something like this here. So I know that calcium has to be on that black band. So let's say that I pick this color. So it goes right here, and then right here. So this guy represents calcium. So this region right in here, this tells us that that is calcium, which has an NP equal to 1. That's calcium. And then I go look at the next atom. The next atom is silver. If I look at silver, I look at that ratio here. And what I see here is that I know that the numbers here, you could see here is that the numbers here is that it's what? It's 47 and 61. So let's go to 47. And I'm going to kind of guess here. Here, let me make sure I got my numbers right. So calcium has around 60, and this is around 47. So how about if I choose a different color here? So then it's got to be let's say this is it right here. So then this number here is 47. By the way, I should have written 20 and 20. And then when I look at, you could see that silver has 61 nuclei. So I'm just going to say it's 60. Okay, and so then this number is 61. But if I look at this guy, this says that the NP number is in 1.3. So you can see how it's moving away from that line. And this is silver. And then finally, there's lead. And lead is all the way at the top. So lead, if I look at the numbers, there's 125. So what I'm going to say here is that since lead is the very last one, I got to bring that right here. Oops, wrong color. So I'm going to say that this is 82, and then look at the number of neutrons, 125. So if it's 125, I'm going to say that this is 125 right here. And this is 125. So then this number right here is NP, and that's equal to 1.5. So that's what this graph is really showing us when I get these nuclei on this table. So they're clearly showing the trend.